Hey everyone! Before we get started with our typical note sheet for today, I just wanted to give you a little background on where we're headed. So the lesson for today is about complex numbers. If you don't know what a complex number is, it may be because it's been a while since you've seen it, or because it's sort of hidden from us for quite a while in our math careers. So if you remember, probably somewhere when you first were introduced to algebra, you talk about a number classifications and you're told that every number is a real number. So you have the real numbers of the world, and then those real numbers break into a couple of subgroups. Some of our real numbers are rational, which means we could write them as fractions. Some of our real numbers are irrational, and then those irrational numbers are the ones that we can't write as fractions. And then the rationals, we now have some more subgroups. If we take out the fractions and decimals and just talk about our positive and negative whole numbers, we have our integers. If we take out the negatives, we start at 0, we have our whole numbers. And then if we take the 0 out of the group, then we have our natural, or what we call our counting numbers. So when you're first introduced to a number classification, you're told again that every number is a real number. Now that's not actually true. The truth is there's a hierarchy here, and it's that every number is not a real number, but every number is a complex number. And so the complex numbers are the top of the number food chain, where part of the complex number is the real number, and the other part of the complex number is the, if you didn't know already, the imaginary number. So when we put the imaginary number and the real numbers together, we have what we call the complex numbers. So technically every number is a complex number. So before we talk about complex numbers and put the reals and the imaginaries together, I think it'd be a good idea for us to talk about just this side of the category. What is the imaginary number? What does it allow us to do? And then what happens when we put the imaginaries and the reals together, and how do we deal with those complex numbers? All right, so to our typical note sheet here. The imaginary number, we're going to call that I. So the imaginary number I is defined for us as the square root of -1. Now when you're writing the I, you have the option of doing a cursive I, as I did a second ago. Sometimes you'll see it written like this, where it sort of looks like a backwards J. What we do not want to do when we're writing our I is just do a simple I like this, or even a capital I. The acceptable ways to write it again are the cursive or as that backwards J. So it's defined for us as the square root of -1, and we have a second definition that we'll use in a little bit, and that is that I squared is equal to -1. And what this imaginary number I allows us to do is it allows us to simplify. It allows us to simplify negative square roots. So keep in mind, if we're evaluating, for example, if we're evaluating the square root of -25, if I asked you for a real number value for the square root of -25, that still does not exist. But if we wanted to now simplify the square root of -25, we could. So when we were simplifying radicals before, we said we can split this up. Instead of looking at -25 as -25, if we say look at it as 25 times -1, then we could say that that's the same as the square root of 25 times the square root of -1 separately, because each of those things has a square root. The square root of 25 we know is 5, and the square root of -1 was just defined for us as I. So we could say that the square root of -25 simplifies to 5i. So again, if we're evaluating, the real number value for the square root of -25 still does not exist. But now if we have a negative underneath our square root, we can simplify using our imaginary number. So basically what happens when we're simplifying negative radicals, specifically negative square roots, the negative is going to come out of the radical as an imaginary, as an I. So the negative comes out of the radical as an I. So if we were trying to simplify positive square root of 7, we wouldn't be able to, but because it's negative, that negative is going to come out as an I. So we could say that this is equal to I times the square root of 7, or you could see it as the square root of 7 and then the I. I prefer to write it the first way because it's very clear there that I is not underneath the radical anymore. You can write it after the radical, but just be clear that the radical ends and that the I is after. Now if we were going to break down 50, let's pretend it was a positive 50 for a second. So 50 is 2 times 25, and 25 is 5 times 5. So if it was a positive 50, we would take out a 5 and we would leave a 2. Now because it's a negative 50, we're going to take out a 5, we're going to take out the negative as an I, and left over we have a 2. So 5I radical 2 is a simplification there. I'll give you an opportunity to try the 6 radical negative 40, and I'm going to work along with you here. Okay, so on this one, we've got a 6 that's already outside of the radical. That's going to stay. Now we're also going to be bringing out a 2. Because we've got a negative underneath, we're also bringing out an I. And then left over in this radical, we still have a 2 and a 5. So this is going to simplify into 12I and then radical 10. I'm boxing these and not this. Let me box these in as well. Okay, so here we have an operation to handle first. The real number operations don't apply to these, what we call imaginary numbers now. So we want to simplify these radicals before doing anything else. So instead of leaving this as a radical negative 12, we're going to make this I, radical 12, and the same thing here. This becomes an I and a radical 3. And now we can multiply the I on the outside to make an I squared. And we can multiply the 3 and the 12 on the inside to make that a radical 36. And then we can actually simplify both parts of this. So not only was I defined as the square root of negative 1, but I squared we defined as negative 1. So I squared is going to get replaced with negative 1. And the square root of 36 we know is 6. So this is going to simplify into negative 1 times 6, which makes our answer a negative 6. Okay, I'm going to give you a chance to figure this one out. Okay, so similarly here, we would take the negative out of the first radical. So on the top, we're looking at I and then radical 18. And then on the bottom, we have our radical 3. And those can be divided. So the I out front here divided by 1 here is still going to be an I. And then we have a radical 18 divided by 3, which makes it a 6. And since that can't be broken down any further, then I radical 6 would be our answer. Okay? So those are our imaginaries. We have a little bit of, hopefully, background, maybe some recollection of it if we've seen it before. Now the goal would be to, again, handle the complex number. That's where we put the real and the imaginaries together. So a complex number has a real number part, and it has an imaginary number part. So that's where we put the reals and the imaginaries together. And we have what we call a standard form for a complex number. So we're going to say it's A plus BI, where A is that real number part and the BI is that imaginary number part. So technically, as I mentioned a little while ago, that every number is a complex number. Every number is a complex number. So 2 plus 5i is very clearly a complex number. Here's the real number part. Here's the imaginary number part. So we put those together. There's our complex number. Now, if you're looking at something like 3 and asking yourself, how is 3 a complex number when I only see the real part there? Well, if we only see the real part, it's because the imaginary part is zeroed out. Oops, pen's going crazy there. So this is really the same thing as 3 plus 0i. So the imaginary part is just zeroed out of that complex number. And the same thing with 7i. So 7i looks like just an imaginary number. But if we put a plus 0 in there, we see the real number part of that is just zeroed out. So here's our imaginary part here. Okay, so every number we could say is a complex number. If we only see the imaginary portion, it's because the real portion is 0. If we only see the real portion, it's because the imaginary portion is 0. But every number has that real and imaginary number part. All right, so operations with complex numbers is basically what we got to be able to handle. And it's pretty simple because we're going to be treating I like we treat x or any other variable. So we're going to treat I like we treat x or any other variable. So here it's basically combining like terms. We would treat the 4i and the 8i just like we would treat a 4x and an 8x. So we've got this negative 2 plus 4i here. If we distribute the negative here, we're looking at a negative 6 and a positive 8i. And then we're combining like terms. So we're going to combine the real number parts. The negative 2 and negative 6 makes a negative 8. We're going to combine these imaginary parts. So the 4i and 8i makes 12i. And that's it. That's our complex number answer if we're subtracting those two complex numbers. Now, it would be okay to say 12i minus the 8. It's not wrong because it doesn't change the value of that expression, but Our complex numbers have that standard form, which is typically how we want to write it. So we want the real number part to be first and the imaginary part to be second. That's the proper way to write it, although these are equivalent. It's just preferred to put it in standard form. Standard form is preferred. Okay, so if we're going to add or subtract complex numbers, we're literally just combining like terms, combining real number parts, combining imaginary parts. Here we've got some multiplication. So 7i times 1 would be just like 7x times 1. 7i times 1 then is just going to be 7i. And then when we multiply here, if we were multiplying 7x and 4x, we would have a 28x squared. Well, here 7i and 4i is going to make a positive 28i squared. Now, anytime we see the I squared, we're going to be using the definition we talked about on the front, because I squared was defined for us as -1, right? From the front, I squared was equal to -1. Anytime we see an I squared, we're going to replace it with -1. So here we're looking at 7i plus 28 times a -1, which means we have 7i minus 28. And just to put it in standard form, we're going to make that a -28 plus 7i. Okay, same thing here, 3 minus 9i squared. So 3 minus 9i squared means we got to multiply 3 minus 9i by itself. And then we're going to go through our distribution. So 3 times 3 is 9. 3 times -9i is a -27i. Here we get another -27i. And at the end of this, a -9 and -9 makes a positive 81. I times I makes I squared. So we've got 9 here. These are like terms. We can combine the -27 and -27 to make -54 in front of I. And then because this is really 81 times, let me move that up a little. Because this is really 81 times I squared, or 81 times -1, it becomes a -81. And now we can combine those real number parts. So final answer, 9 minus 81 is going to be a -72. And then minus that 54i. Okay. Now 7, we see we have some division, but I can't actually divide 5 by 2 or by I. So the approach we want to take here is a similar approach that we took when we were looking at radicals, so rationalizing the denominator of a radical. So if, for instance, we had something like 5 divided by a radical 2, we were trying to multiply by something that would get rid of that radical. It's a similar process here, which should make sense because I really represents a radical. If we want to make the I go away, we're going to multiply by an I and an I. So technically multiplying by 1, not changing the value of the fraction, but what happens is on the top, 5 times I is 5i. On the bottom, 2i times I is going to give us 2i squared. And because I squared was defined for us as -1, this 2 times -1 on the bottom means we can simplify this to 5i over -2. Okay, so if we've got an imaginary number on the bottom and we can't divide it, then we're going to, sort of like rationalizing, we're going to multiply the top and the bottom by I to get rid of it. Now number 8 looks a little different, right? Number 8, we can't again divide 12 by 1 minus 3i, but we can still simplify this. Again, similar to what we did when we rationalized denominators. If we multiply here by the conjugate of our denominator, if we multiply by 1 plus 3i on the top and the bottom, we can get rid of that imaginary from the bottom. So on the top, the 12 times 1 gives us a 12. 12 times 3i gives us 36i. On the bottom, so 1 times 1 is 1. The positive 3i here and negative 3i here are going to cancel, so we can skip those guys. And then negative 3i times positive 3i gives us a -9i squared. Now this is really going to be 1 minus 9 times -1 here. And so that's really going to be 1 plus 9, which means our fraction becomes 12 plus 36i all divided by 10. Now because the 12, 36, and 10 all have a 2 in common, we can reduce this. Reducing or dividing all three of those terms by 2 leaves us with 6 plus 18i all divided by 5. So that would be acceptable there. And I'm okay with you leaving it that way. Just recognize if you wanted to separate that out, that this would be equivalent to, let me go over here. This would be equivalent to saying 6 is being divided by 5 plus 18i is being divided by 5. So it'd be okay to write it as two separate fractions. Sometimes that way is preferred if, let's say, only 2 of your parts are reducible. So for instance, if you had something that goes in, it's not a good example to show that, but if for some reason one of your fractions reduced and the other didn't, it would be preferred to write it as 2 separate fractions to be able to reduce the one. But either way is acceptable, 1 fraction or 2 separate. All right, let's look at this one. Again, we're going to multiply by the conjugate, so 10 minus I on the top and the bottom. So 9i times 10 is going to be 90i, and then 9i times negative 1 is going to be a negative 9i squared. On the bottom, 10 times 10 is 100, and then negative 10i, positive 10i cancel, and then I times negative I is going to be a negative I squared. So now we have I squareds in the top and the bottom. So this becomes negative 9 times negative 1, or positive 9. And this becomes negative times a negative 1, which makes it a positive 1. So final answer, let's see. We've got 90i on the top, plus we have a 9. On the bottom, 100 plus the 1 is 101. And not reducible, but just that it's in standard form. I'm going to make this 9 plus 90i over 100. Not 100, 101, so 101. And that's going to be our final simplification there. Again, if you wanted to separate that and say 9 over 101 plus 90i over 101, that would be acceptable. Okay? Now, if you look at number 9, we can actually do some division. Just like if that was 30x to the 7th over 6x to the 3rd, we can divide the coefficients, so the 30 divided by 6 would make 5, and we could subtract our exponents here. So 7 minus 3 would leave us with an I to the 4th. The issue is higher powers of I are not defined for us. So what we have definitions for are I to the 1st. I to the 1st we said was the square root of negative 1. And we have a definition for I squared. I squared we know is negative 1. But anything beyond an I to the 1st or an I to the 2nd power, we're going to have to simplify that further. It's not defined, so we have to get rid of it. So what we want to do with a higher power of I is think about it in terms of I squareds, because I squared is one we can get rid of right away. So for example here, instead of leaving this as 5i to the 4th, this is 5, and then I squared how many times? How many times do we have an I squared in I to the 4th? Well, if I take the exponent of 4 and divide it by 2, that tells me it's I squared twice. Right, so I squared squared would get me that I to the 4th. And the reason I want to do this is because I squared we can get rid of. So this is really 5 times instead of I squared squared, it's negative 1 squared, and that can be simplified. Negative 1 squared is positive 1, so this is really just 5 times positive 1, making our final simplification 5. Okay, so if you have a higher power of I, you're going to simplify it by rewriting it in terms of I squared. So for example here, I to the 43rd is I squared how many times? Well, this one doesn't divide evenly, so if I took 43 and divided it by 2, 2 goes into 43 how many times? Well, 2 is going to go into 4 twice, it's going to go into 3 once, but that's only 42 times, so then there would be a leftover, like an extra I left over, I to the 1st left over. So altogether we're looking at, that's 42 i's plus the 1 that we have there, that's 43 altogether. So I to the 43rd is I squared 21 times and then an additional I. So if I simplify this, this is negative 1 to the 21st, and there's that leftover I. And negative 1 to the 21st power, that's just going to be a negative 1 in front of that I. So a negative I would be our simplification. Okay, trying that again. So this is the same as 2, then I squared how many times? So 61 divided by 2 is 30 with 1 left over. So there's your 60 and 1 to make 61 altogether. Okay, so this becomes 2 times negative 1 to the 30th power times that leftover I. So 2 times negative 1 to the 30th power is going to be a positive 1. So 2 times 1 times I makes this answer a positive 2i. Let's keep the equals in all those. Okay, so positive 2i is that one. And then last one, I to the 86th power, this is I squared how many times? Well, I squared, 86 divides by 2 exactly 43 times. So I squared times 43. And now we're looking at negative 1 to the 43rd power. And negative 1 to the 43rd power is just a negative 1. So this simplifies to a negative 1. Okay, I think that covers it. I know I went kind of quick, but because this is recorded, you have the option to go back and watch those again. And if you have any questions, just reach out, email me, let me know. Have a good one.